Hello and welcome to Mathematics Tutorials and Tricks. Today's lesson is the first lesson in a series of lessons about loci, in which case we're going to look at the objectives that are on the screen there. But this lesson and two others are going to be dedicated to definition for loci. So we're going to define what loci is in 3 videos. And so let's begin with the first one. Loci really is a word that's associated with the word location, as I understand it. Loci and locus are such that loci is the plural of the word locus. Locus is singular, the same way we talk about radius and redi, or alumnus and alumni. And therefore, loci is really a path, an area, or a volume traced out by a point, a line, or a region. Respectively, it moves according to some law or laws. So a point traces out a path, a line traces out an area, and a region traces out a volume. That's why I put the word respectively here. As that point or line or region moves according to some law or laws. And let me explain that this way. Infinite points trace out a path. If you have many points next to each other, that's what we call a line or a path. For example, we have those points appearing on your screen there. If these points are infinite and many next to each other, they will form a line like the one that we have there. But to illustrate, I've just picked few points. Many points would form a line. Similarly, infinite lines trace out an area. If we have these many lines next to each other, they'll form an area of some kind. If we have a line like that, another one, another one, another one. If we have many lines next to each other, they form an area. In this case, some sort of a rectangle, really. So if you have as many lines, infinite lines, they can form an area. And I think that's clear. Now, similarly, if we have many regions, that is areas, they trace a volume. For example, if we have, say, this is a rectangle, we are seeing it in 2 dimensions, but it's 3 dimensions. So this is a rectangle. Let's place it again, another one on top there, and again another one, and many others. They will form some sort of a volume. The same way we have pages of a book forming the volume of a book, which has some sort of a length and a width and a height. And therefore, many regions or areas will trace a volume. They might not be arranged in any particular order like this, but if they are arranged in some sort of order, which we call now the law, then they form what we are defining as loci. This might not be as clear already to many of you, but this is really the definition that someone should understand, so that they say they have an understanding of what loci is. So that path or that area or that volume that is traced out by a point or line or a region according to some law is what we call loci. As we move on, we are going to consider some common loci we encounter in mathematics. And so let's begin with common loci. The first one is a perpendicular bisector. We are already familiar with how to bisect a line and things like those. But now look at this. All points P which are equal distances or equidistance from point A and B trace out a perpendicular bisector of the line AB. Let me illustrate that this way. We have a point A and a B. All points which are equal distances simultaneously so from A to B, from A and from B, then they are perpendicular bisectors of the line AB. For example, let's have a point P such that this distance from A to P and the distance from P to B, they are the same length, say 7. Let's have another point P, say that one there, and the distance this A to P, P to B is a constant number, say 8, so that this is 8, this is 8. Let's have another point P such that the distance from A to P and P to B is a constant number, say 5. Or another point there where they say this distance and this distance is the same, say 10. Maybe another one like that. The many points we could form which are simultaneously equidistant from the points A and B. they trace a perpendicular bisector of the line segment AB. That means the points P, all of them form a line which coincidentally perpendicularly bisects line AB. And by the way, perpendicular bisector has two important words in that statement. Perpendicular means that line meets the line AB at 90 degrees. That's a right angle. Bisector means divides the line AB into two equal parts. So the two words are really key just to define what you're talking about. Let me say this, therefore, that the set of points P equidistant from points A and B is a perpendicular bisector of a line, or those points which are equidistant from A to B form a perpendicular bisector of the line AB. In 3 dimensions, that set of points P form a plane. If this you are envisioning or looking at this in 3 dimensions, P will not be a line, but rather a plane. If you have a point A and another point B, and there's a line segment there, the set of points which are equidistant from A to B could be anywhere in this plane. So we would say that this plane is a plane which perpendicularly bisects the line segment AB. Let's move on to the second one. Points equidistant from a line. So if you have two points A and B which form a line, all points which are equal distances from the line AB are parallel lines to the line AB. And let me explain that. All points P equidistant from line AB trace out the parallel lines to the line AB. And therefore, let's say it this way. Say we have the line AB. Say we have a point P. We have another point. We have another point. I'm calling all of those points P here. We could also have them below here. And they're all of them such that the distance from P to the line AB is same as the distance from P to the line AB, same as the line P to the line AB, is same as P to the line AB, such that all of these perpendicular shortest distances, all of them, if all of these distances are the same, then P is a sort of many points forming a line over there, or many points forming a line such down there, such that this line is parallel to AB, and this other line here is also parallel to AB. And what I'm saying is that we could, when we're talking about P, we are talking about a set of points above line AB which are parallel to the line AB, or below the line AB which is parallel to the line AB. And therefore, I would say that a set of points P equidistant from the line AB are lines parallel to the line AB. In 3 dimensions, that set of points P form an open cylinder. In this topic, we are supposed to imagine a lot. And therefore, I want you to imagine for a moment, what would this be if we were talking about 3 dimensions? We'll be having a line like that is the line AB, and we'll be having a cylinder such that all points on the cylinder, an open cylinder in this matter, all points on the open cylinder are equal distances, such that if a point P, say, is at that point there, the shortest distance to line AB is same as another point, say here, shortest distance from that point to the cylinder, and all through. It is infinite number of points which are equal distances from the line AB, such that a point P to the line AB, a point P to the line AB, the shortest distance between the two of them is the same in all cases, wherever P is. So those sort of points parallel lines to the line AB, and I think that's that. Let's go to the third case. Points equidistance from a point, and let's say this: if we have a point A, then all points P which are equal distances from A, they trace out a circle with a circle center being A and the radius is AP. Let me say that again in this particular way. Let's say we have the point A, we have a point P, we have another point P, another one, infinite number of them. I have only 5 points here, and there are all of them such that the distance from A to P, whatever P we're talking about, if that first one or this other one or this P or that other one or that, if all of those P's are the same distances, then what you're talking about here is a set of points which are on the circumference of a circle whose center is A and the radius is AP. and that is a circle there. The points P lie on the circumference such that AP is a radius and A is a center. The set of points P equidistant from a point is a circle with radius AP, as I have said. Again, in 3 dimensions, this would be a sphere. In 3 dimensions, that would be a sphere. An angle bisector to a loci. This is the last one. An angle bisector loci. And so, let me say this. If we have a line AB and XY, they are intersecting at a point M. Therefore, all points P, which are equidistant from the line AB and XY. You see, the line AB and XY simultaneously, they are the bisector of the angles AMX and YMB. A very loaded statement. Let me break it down. Say we have a point P such that this shortest distance to the line AB and this shortest distance to the line XY, they are the same. They are C. We have a point P. Let me go over it again. We have point P such that that shortest distance from the point P to AB and P to XY, if those distances are the same, say C, and say we have another point P such that the shortest distance from P to XY and the shortest distance P to AB, again they are a constant number D, and we have many other points like those. Those points will, all of them joined, form the angle bisector, the bisector of the angle AMX and YMB. This line here, we have many points P which joined would form the bisector of those two angles, AMX and YMB. Therefore, the set of points P equidistant from a line AB and XY are bisector of the angles AMX and YMB. Again, the same thing would happen if we had a set of points which are equidistant along this one here. There will be bisector to AMY and XMB. I hope you find that helpful. Check out for the next lesson and the next lesson, which are also and more explanation of this. The next lesson will be about tackling questions on this, and the last one will be a particular lesson that will be done using another application to help understand the concepts of loci all the more. Thank you.